Okay, so today we're very happy to have Scott Collier from Princeton PCTS, who's going to be telling us about some interesting new developments in N=4 ADS5 cross S5.
Great. Well, thanks very much to the organizers for the invitation. It's great to see a bunch of friendly faces in person. Very novel. So today I'm going to be telling you about this project we finished, I guess, over a month ago now, with Eric Perlmutter at CA Saclay. And it's actually building on a project we did in the summer with Nathan Benjamin, Alex Maloney, and Liam Fitzpatrick in a different context, using similar tools in the context of partition functions of 2D CFTs. And here we'll see they have a much more natural home in the context of N=4. So the goal of this talk is to understand the physical consequences of S-duality and N=4 superunions, and we'll see that along with that, there are some interesting implications for holography. So obviously, at the risk of stating a tautology, N=4 is an extremely beautiful theory from a myriad of perspectives. You know, it's a maximally supersymmetric gauge theory in 4D, which leads to a very rigid structure of the CFT data. And over the years, it's been approached by a wide variety of perspectives. There's perturbation theory, complemented in recent years by modern bootstrap techniques. For supersymmetric observables, you have localization, and then at large N, you have integrability. And of course, a big part of our underlying motivation here is that via ADS CFT, it furnishes our most explicit and robust definition of non-perturbative monography. But the important aspect of N=4 for this talk is that it enjoys S-duality. S-duality is a non-perturbative strong-weak coupling duality. So just to give some context, N=4 has a one complex dimensional conformal manifold, superconformal manifold that preserves the N=4 supersymmetry. And a coordinate on that conformal manifold is the complexified coupling tau. Its real part is the topological theta angle of the gauge theory, and its imaginary part is 1 over the gauge theory coupling. And the statement of S-duality is simply that CFT observables, which throughout this talk I'll denote very abstractly by O of tau. This is not an operator, it's an observable, like a 4-point function or a dimension of some local operator, and it depends non-holomorphically on tau. I'm just omitting the bars because just for convenience. And so the statement of S-duality is that these observables O are invariant under SL2Z transformations of tau. And importantly, you can do computations at weak coupling, but really this is an inherently non-perturbative duality. And in fact, its existence is kind of obscured in the Atoft limit where you zoom in near the cusp.
Sorry.
Yeah.
Aren't observables fall under representations of the symmetry rather than being invariant?
That's right. If observables are covariant under SL2Z, then that can be accommodated by this framework. But for the purposes of this talk, I'll restrict my attention to observables that are fully SL2Z. And something I just want to emphasize as a bootstrapper is that this is a symmetry that has not really been used. It's not really been taken advantage of. And what would it mean to take advantage of it? It would mean to process it at the outset of calculations and reduce all of CFT observables to their dynamical content. And that's what we'll try to do in this talk. So yeah, I said this earlier, but in practice, we have very little concrete information about the modular structure of CFT observables to complement perturbation theory. So the idea of this project was simply to bake in, it's kind of the dumbest thing you could imagine, just bake in modular invariance at the outset of all calculations and reduce CFT observables to their dynamical content. And within this framework, explore the consequences of S-duality. And our main tool will be robust spectral theory on the fundamental domain of SL2Z. And within this framework, we'll see that it gives a quite novel presentation of CFT observables, and we'll see that once this framework is set up, very simple calculations will lead to some pretty interesting insights about both perturbation theory and the structure of the instanton expansion. And in particular, we'll see that the structure is quite rigid at large N in the Atoft limit, where one fixes the Atoft coupling. In particular, we'll see that SL2Z invariance will imply the existence of non-perturbative effects, both at large N and at strong coupling. Now, of course, at strong coupling, planar n equals 4 is famously dual to type 2b supergravity on ADS5 times S5 with a prescribed set of stringy corrections. And perhaps surprisingly, S-duality has something to say about this. And the main take-home message is that the large n limit of ensemble averaged, in a sense I'll define shortly, n equals 4 super Yang-Mills is the strong coupling limit of the planar theory. In other words, ADS5 times S5 supergravity. We established this at the level of observables O, which are themselves SL2Z invariant. So this leads to an embedding of recent ideas that have been floating around in the low-dimensional quantum gravity literature recently on ensemble averages and averaged holographic duality within string theory. So we'll see that we'll be able to study statistics of observables within this SL2Z ensemble, and this will lead us to speculate about the role of wormholes and the factorization puzzle within n equals 4. So we have this cartoon down here, this abstract cartoon. M is the moduli space. It's this teardrop region. Up here at this point is the cusp. So we have these two equivalent representations of supergravity, both as a strong coupling limit and as a large n limit of the average, which I've denoted by this shading. So the slogan is that this leads to an emergent averaged holographic duality within string theory.
When you say average, you're averaging, well, you're going to tell us what you're averaging.
I should tell you now. So I told you previously that n equals 4 has this conformal manifold. It's labeled by this complexified coupling. We'll perform an ensemble average of that coupling with respect to the Zamolodchikov measure on the moduli space. So with the measure inherited from the Zamolodchikov metric on moduli space, and that's the sense in which I mean ensemble average n equals 4.
And then you'll average over tau.
Yeah, exactly. Yeah, over couplings and theta angles.
So these supergravity observables are independent of the string coupling, basically.
Well, I'm taking the strict supergravity limit, so I'm sending the Atouf coupling strictly to infinity. There's a 1 over n expansion, of course, and we'll establish a correspondence at each order in the 1 over n expansion.
Okay, so there'll be data about.
Yeah, at each order in the 1 over n expansion, we'll establish a correspondence between an average and a leading supergravity answer, in a sense that I'll describe in a bit. Any other questions? Okay, so the hopefully not too ambitious outline for the talk is the following. I'll start by reviewing the spectral theory of this SL2Z spectral theory tailored for n equals 4 observables. I'll give what I think is a really beautiful and concrete example of what I mean when I say CFT observable, which is this integrated stress tensor multiplet 4-point function of Binder, Chester, Pufu, and Wang. Then I'll describe how perturbation theory, the well-definedness of perturbation theory, leads to strong constraints on the analytic structure of the spectral overlaps, which are really the dynamical data in this spectral presentation of observables. Then I'll finally get to large n and the Atouf limit. I'll hopefully have time to discuss the non-perturbative effects at large n. And then that will lead us to supergravity as an emergent ensemble average. We'll study statistics within what we call the SL2Z ensemble, the space of complexified couplings tau. And we'll conclude with some remarks on what this means for ADS CFT and the role of wormholes in n equals 4. Okay, so I've included here a cartoon of the keyhole fundamental domain of SL2Z. This is really where you should think of the complexified coupling tau as living. I'll write tau as x plus iy throughout the talk, so that x is basically the theta angle and y is 1 over the Yang-Mills coupling. There's a natural metric on this moduli space, which is just the usual hyperbolic metric on the upper half plane. And it comes equipped with a Laplacian, which is the following differential operator. And that will be important for us because there's a natural inner product on this space with respect to which that Laplacian is self-adjoint. So it's simply given for two functions f and g by integrating them over the fundamental domain with respect to the usual Poincare metric. Now, the basic idea of this project was to decompose these abstract observables, which I call O of tau, into eigenfunctions of the Laplacian using this inner product. Now, the Laplacian isn't necessarily something super physical or important from the n=4 point of view. It's what moves you around on moduli space, of course. But really, we're just taking advantage of the fact that there is a complete basis and that we understand. And so we're going to use this basis. Now, this decomposition, which I'll refer to as a spectral decomposition throughout the talk, is possible when the observable is square integrable with respect to this Peterson inner product. This is what didn't work for CFT partition functions, but it turns out to be rather generic for n=4 observables for the simple reason that, observables are finite on the interior of moduli space. You have to worry about boundaries, and in particular, you have to worry about the cusp. But here, the cusp, when you take tau to I infinity, so that's like taking the weak coupling limit, G angles to 0, that's just the free limit. So as long as the observable has a well-defined free limit, then it fits into this framework.
So should I think about these observables as functions of positions as well?
Yeah, they may have a ton of other labels that I'm suppressing. The only label I'm keeping is its dependence on the complexified coupling.
Well, why is it like a uniform dependence on tau then? In the sense that I could imagine a tree-level function independent of tau plus something with its own modular function of tau plus something with its own modular function of tau, et cetera. That's ruled out for some reason, or?
No, I think that fits into this framework.
That was
It depends
still-
on what you mean, which loop expansion you're referring to when you say tree level. And
Yeah,
I
good.
assume you mean 1/n or something like
No,
that?
well, I was actually thinking from the gravity perspective, where it'd be supergravity plus some correction.
Right.
correction,
Yeah.
correction.
We'll see. That fits into this framework.
But they'll have different position dependence for each function of tau then.
Yeah. The spectral overlaps will depend on the.
Oh, maybe you say you don't care. You just analyze any given term.
All I'm saying is that we can use this basis to package the dependence on tau, and then the only dynamical data that's left are these overlaps in this basis.
Okay.
And I'm suppressing all these labels because I want to talk about general observables. So, they may depend on positions, they may depend on like operator dimensions.
Can you elaborate on the square integrability? I mean, just having a good limit at tau equals I infinity is not enough, right? The region is non-compact.
That's right, but I think as long as there aren't singularities in the interior of moduli space, then
If, like the function was constant. If O is constant, it wouldn't be square integrable.
no, it has finite volume. It's non-compact, but it has finite volume with respect to
it's
that.
gonna be-
Y squared in the denominator.
Yeah, exactly. So that is what facilitates this, and it's important for a part of the basis that I'll describe soon.
You say nice harmonic analysis should work here.
Yeah, that's the idea. Any other questions?
You said this is something that didn't work for CFTs. What did you mean?
Yeah. So CFT partition functions at the cusp, they grow exponentially. The vacuum will give a divergent contribution as you take. Okay, the tau is no longer a complexified coupling in that case; it's the complex structure of the torus. But as you go to I infinity, the contribution of the vacuum will give you a divergent.
By CFT, you mean 2D CFT.
Yes. In that context, here I'm talking about n=4, but yeah. Very good. Okay, so here's the basic idea. I decompose the observable into these three branches of the complete basis of eigenfunctions. So first, there's the constant with eigenvalue 0, obviously. I'll elaborate more on each of these in a second. Second, there's a continuous branch, which is spanned by these funny functions that are called the real analytic Eisenstein series. They have this eigenvalue under the action of the Laplacian, and they're delta function normalizable when S takes these values. And finally, there's a set of an infinite but discrete branch spanned by the so-called Moss cusp forms. They have these eigenvalues where the t's are a set of sporadic real numbers. And these are actually normalizable with respect to the Peterson norm. And their existence may be surprising because of the non-compactness of the moduli space, but it's again related to the fact that the fundamental domain is finite volume. So there's a Weil's law for the growth of these eigenfunctions.
Sorry, is T1 to T2, etc. These are known numbers or?
Yes, they're in principle, they're not known exactly. They're known to 1,000 digits, and they can be determined by a bootstrap-like procedure. But they're not known analytically, but they're known for practical purposes numerically. Okay, very good. So the real analytic Eisenstein series, these are formally defined by Poincare series, a sum over SL2Z images of the imaginary part of tau. This converges when the real part of S is sufficiently big, but the function satisfies a functional equation which allows you to extend this regime, and moreover, there's a meromorphic continuation to the entire complex S-plane, which is facilitated by its explicit Fourier decomposition. So here I've defined E star, which is symmetric under these reflections, S to 1 minus S. Here, capital lambda is this funny function involving the zeta function. It's like a completed version of the Riemann zeta function that satisfies this functional equation. The explicit form isn't important, just that there's a zero mode, which is known explicitly, and there are higher Fourier modes. And a small comment here on the Fourier decomposition. In n equals 4 language, because I'm doing a Fourier decomposition with respect to the real part of tau, x, which recall is the theta angle, this is an expansion in instanton sectors. So k equals 0 is the 0 instanton sector. In 0 instanton plus instanton anti-instanton and so on. And these are sectors with total instanton charge k. Now, this discrete branch is much more wild and mysterious, and they turn out to be related to the energy eigenstates of the quantum mechanics of a particle propagating on the fundamental domain, which is known to be a classically chaotic system. Their functional form is morally very similar to the continuous branch that I just wrote down earlier, with two important differences. First is the absence of a zero mode, so note that the sum here starts at k equals 1, there's no zero mode. And moreover, they decay exponentially at the cusp as you take y to infinity. That was not true for the Eisenstein series. You had the zero mode, which grew polynomially at the cusp. Now there's some data here. There's the eigenvalue, which remember was labeled by these numbers Tn, which shows up here. And there are also these Fourier coefficients, AK. These are a set of sporadic real numbers whose statistical properties are of great interest to mathematicians. And sort of the body of work that studies these quantities goes under the name of arithmetic quantum chaos. There's a lot more that one can say about these, and it'd be interesting to explore the connection between this notion of chaos and more conventional spectral or dynamic notions of chaos and n equals 4. But for the most part, we won't explore that in this talk. So here's a plot.
Asymptotics at large n is known?
Yeah, that's right. The eigenvalues themselves, for reasons related to this word arithmetic, the fact that it's an arithmetic, the fundamental domain is an arithmetic surface, they turn out to exhibit Poissonian statistics asymptotically, whereas these Fourier coefficients exhibit statistics that is more evocative of like random matrix theory. I can be more precise after the talk. So here's a plot just to get across this idea that they're wild. So here I'm plotting the zero mode of the square, and the reason for that is just because it's a quantity that involves all of the Fourier coefficients, and so it sort of captures the wildness. Blue, yellow, and green are the cusp forms, and this red curve here is the same quantity but for the Eisenstein series on the critical line. And these curves have some sporadic set of extrema. There doesn't seem to be any rhyme or reason to them, and they appear much less smooth than the Eisenstein series. Okay, so the basic upshot of this discussion is that observables admit a unique decomposition in this basis. So there's a constant, Eisenstein series, cusp forms. And all the dynamical data of the observable is packaged in these overlaps, these inner products with the eigenbasis. Now, I call the constant part O bar because it is the modular average of the observable over the fundamental domain. So I take the observable and integrate it over the fundamental domain. This Eisenstein overlap, on the other hand, if you take advantage of the fact that the Eisenstein series is a Poincare series, you can write this integral over the fundamental domain as a Mellin transform that only involves the zero mode. So the point is that this quantity here is determined entirely in terms of the zero mode. And that will be important in what follows, because under some favorable circumstances, these guys will vanish. So in a sense, the entire observable is determined by its zero mode in these contexts. So there's some immediate consequences of this. The first is that the overlap with the Eisenstein series satisfies a functional equation under reflection. So I define this funny bracket O, where I divide by this funny lambda function, and then that's invariant under reflections. And that's just inherited from the Eisenstein series. Importantly, this constant term, which remember was the modular average, is also the ensemble average of the observable over the conformal manifold with respect to this measure inherited from the Zamolodchikov metric. And the reason for that is essentially due to maximal supersymmetry. So I define the ensemble average by integrating over the conformal manifold with respect to this measure, but because of maximal supersymmetry, this measure is just the Poincare measure. So it's the exact same as the modular average. So in the spectral decomposition, the ensemble average is cleanly isolated. A final thing, which I was getting at with these comments about the zero mode, is that there's a sense in which instantons are redundant, which is not really obvious from, resurgence approaches to studying like the instanton expansion. So again, I expand the observable in a zero mode plus some higher Fourier modes, which again, remember K labels the total instanton charge. And the point is, these are not all independent. They're tied together by this spectral decomposition. So in particular, in the case where the cusp form overlap vanishes, then you have this basic algorithm where you take the zero mode. Suppose you are able to compute that somehow. You take its Mellin transform, and that gives you the Eisenstein overlap. And then you integrate it over the kth mode of the Eisenstein series, and that gives you the K instanton sector. So this will be a theme that SL2Z relates different instanton sectors in a very simple way. Are there any questions before I move on? I realize that's a lot of background. Okay, so before proceeding with the more general analysis, let's talk about this benchmark observable, the integrated correlator. So yeah, I've said this word CFT observables a lot throughout this talk, and I should say what I mean by that. And what I have in mind in particular is observables that are non-perturbatively well-defined across the conformal manifold. So I have in mind things like correlators of protected operators, the spectrum of the dilatation operator, structure constants of primary dilatation eigenstates, things like that. CFT, things that can be defined in terms of CFT data, essentially. What I do not have in mind is anything that makes reference to the Lagrangian formulation of the theory or relies on large N for it to be well defined. So I do not have in mind, for example, the anomalous dimension of the Kenishi operator.
Why is that not well defined? Is there level crossing?
Yeah, that's basically it.
Even at finite N?
Yeah, I mean, I don't know how to define it at finite N. You can,
something
that would be well defined.
There is a operator that you can identify at zero coupling called Konishi, and you can track that operator unless there's level crossing.
That's right. What I have in mind is what I would prefer to talk to rather than Kenishi is like the lightest scalar SU4R singlet primary operator. That would fit into this. The dimension of that operator would fit into this framework. So just to give an example, which I view as extremely beautiful and really provided a benchmark for this work, is this integrated 20 prime stress tensor multiplet 4-point function of Binder, Chester, Pufu, and Wang. So I call it Gn of tau. What is it? So I take the dynamical part, so I strip off the GFF part of the 20 prime 4-point function, and I integrate it over Euclidean space, U and V are cross ratios here, with respect to some measure that preserves supersymmetry. Now, because it preserves supersymmetry, or a sufficient amount of supersymmetry, this observable also admits a representation as a derivative of a mass-deformed sphere-free energy, which you can compute from localization. Now, remarkably, this observable is conjectured to be known for all n and for all values of tau. And this was in a really impressive, I think underrated paper by Doragoni, Green, and Wen from last year. What is it? It's we refer to this as a lattice integral representation because it involves a lattice sum over two integers and an integral. Now, there's some simple dependence on tau here this exponential, and there's a kernel, which is some rational function of this variable c.
What is the physical interpretation of this formula?
Very good question. It completely obscured in this representation, and we'll see in a few minutes what the physical interpretation is. Or at least we'll ascribe physical meanings to this quantity, this kernel. So for them, this is just some abstract representation that they checked exhaustively against,
So how did they guess it?
by exhaustively studying the zero and multi-instanton sectors from localization. I think they came at this representation first, actually, where they noticed a pattern in the structure of the perturbative expansion of the zero modes, which they then checked the higher modes are consistent with this. So anyway, for them, this is just some kernel, which is some rational function. And I want to emphasize how remarkable it is, like how simple this formula is, because the complexity doesn't really grow with n in any way, other than the fact that the degree of the polynomials in this rational function in the numerator and denominator grows. But other than that, it's the same. Like in localization, you're integrating over the carton of SUN, so that gets more and more complicated as you crank up n. So anyway, there's this representation which they conjecture and tested against as exhaustively as they could. And another more formal representation they have is the following. So there's some constant and there's some infinite sum of Eisenstein series with integer argument s. This is a bit more formal because the sum doesn't really converge for all values of tau, but we'll see how both of these representations can be obtained from the general formalism we'll develop. And there's a simple formula for SU2 for these overlaps, and you can obtain the higher n values from this Laplace difference equation. Okay, so I claim that this integrated correlator fits very nicely into our framework, and it's given exactly by the following spectral decomposition. So remember this constant, n times n minus 1 over 8. Claim that that's half the average. So I claim that this is the value of the average over the conformal manifold, and that this coefficient Cs, so it was originally defined on the integers. If I pull it back to the critical line here, then this combination here, note that this factor here has poles at integer values of s, that this is the overlap of Gn with the Eisenstein series. And in particular, the overlap with the cusp forms vanishes. So it's at least clear how to generate the latter representation from this. You deform the contour.
Why does the inner product with the cusp form vanish? Like not why.
Great question.
Not can I compute it, but why a priori?
We don't know the most general. We don't know the settings under which the overlap with the cusp forms vanishes. It's something we determine experimentally. There's a feeling that it may have something to do with the amount of supersymmetry preserved by the observable, but we don't have a proof or anything like that. It's a good question that we would like to better understand the answer to. You can check it, of course, by looking at the k instanton sectors and checking that it's completely consistent with this. It would be screwed up if there was some cusp form overlap.
But in the four derivatives with respect to the mass operator, there are cusp forms.
Yeah, that's right. Yeah, so what Clay is referring to is that there's another integrated correlator. Well, actually, it's the same correlator, but you integrate it with respect to a different measure. And it's a much more complicated object. We study it as exhaustively as we could in the paper. But yeah, in particular, the cusp form overlap of that thing is non-zero. It's a much more complicated beast than this thing.
If you computed this from a gravity perspective, the same four-point function, in the gravity action, cusp forms don't appear, right? In any known couplings?
They do, starting at D6 r to the 4, and that's related to this.
D6 has a cusp form.
That's related to this. So I'm talking about the effective action of AS5 times S5. This other integrated correlator that Clay is talking about appears actually, or rather, sorry, I shouldn't say it literally that way. There's a function that appears both in that observable and in the D6 r to the 4 coefficient that has non-zero cusp form overlap.
So you should have expected it in general.
Yeah, it seems like a very special thing that would not have cusp form overlap. So anyway, let's talk about how perturbation theory controls or constrains the analytic structure of these spectral overlaps, O E sub S. And so perturbation theory, how do I develop perturbation theory? Here's an expression for the zero mode. See, I've just put in the zero mode of the Eisenstein series here. So, and there are no cusp forms because they don't have zero modes. So how do I develop perturbation theory? Well, I deform the contour. Remember that y is like 1 over g squared. So in the weak coupling regime, I did deform the contour for this term one way and this term for the other. And the statement about the well-definedness of perturbation theory is that upon contour deformation, there can only be non-negative integer powers of y and no logs. Now, you might complain that I'm not really allowed to deform the contour because I haven't said anything about the growth of this thing at large S in the large S asymptotics, and you would be completely correct to complain about that. However, we'll see that the large S asymptotics of this overlap will encode the asymptotics of perturbation theory. So in particular, how this thing behaves as you take S to infinity in either direction, that will tell you whether the perturbative series is convergent, divergent or asymptotic but Borel summable, not Borel summable. All of that you can diagnose by looking at the asymptotics of this thing. So that's the value, I think, of this representation. So I claim that the most general form of the overlap consistent with perturbation theory takes the following form. So there are two functions here, fp and fnp, which are meant to denote the perturbative and non-perturbative contributions. So here I've put in the poles at integer values of s by hand. That's what this pi over sine pi s that we saw earlier for the integrated correlator. That's what that thing does for a living. So the job of this thing is to generate the perturbative series. And there's some regular leftover part. And what that thing does is it generates non-perturbative corrections. So like instanton, anti-instanton corrections. These functions satisfy some nice properties. They're reflection symmetric, regular basically everywhere in the complex plane. And this overlap has to vanish at s equals a half because that's a property inherited from the Eisenstein series.
Sorry, can you just say one more time how you distinguish the instanton anti-instanton contribution from the
So this term has poles at integer values of s. So when I deform the contour, I pick up perturbative contributions, and there are no such poles over here. And so this thing, in a sense, lives on the critical line. You can't really deform it, or you can, but you have to be careful about infinity, and that will generate these exponential corrections, the non-perturbative in the weak coupling limit corrections.
So when you said that instantons are, quote, redundant, you meant, did you mean including this FNP?
Yeah. I had in mind the sectors of different total instanton charge. So remember, this is all in the zero mode. So these are QQ bar corrections. I had in mind redundancy between like 0, 1.
But F sub NP is not computable as G goes to 0? In the strict G, in the
because it's obscured. You have to compute the non-perturbative corrections, the II bar corrections. So I think this presentation reveals that, in a sense, this integrated correlator for SU2, whose explicit form for that coefficient I wrote down earlier, is in a sense an optimally simple observable. So remember the cusp form overlap vanishes. That was true for all of them. Remember the overlap had it had a pi over sine pi s times some function. So the non-perturbative part vanishes. That's true for all n. And the perturbative part was the simplest thing consistent with these constraints that I wrote down here. It's this quadratic polynomial on S. So really we had no reason to expect this a priori, but this integrated correlator for SU2 is really, in a kind of precise sense, an optimally simple observable that's consistent with SL2Z and the structure of perturbation theory. Any questions? So I'll introduce here another tool we developed in the paper, which I think is kind of neat. So in n equals 4, it's often the case that the weak coupling expansion is Borel summable, so asymptotic but Borel summable. So here's some schematic form with some coefficient Cn. some power series in 1 over y. And you can relate these coefficients to the overlaps that I wrote down earlier. So here's FP, and here's that lambda function. So remember, this thing involved a gamma function, so it grows factorially at large n. So you can define a modified version of the Borel transform that knows about the structure of SL2Z invariant perturbation theory. We call this the SL2Z Borel transform, where you just take the same series but strip off this factor of lambda. And if the C's grew this way at large n, then the radius of convergence of this Borel transform is R. And you can pretty neatly obtain the resummation of this perturbative series by inverting this transform using some integral transform for the lambda function. There's some explicit form here. And so this is nice because it lets us make contact with the D'Origoni, Green, and Wentz presentation of the integrated correlator Gn. So remember that when the cusp form overlap vanishes, you can reconstruct O from its zero mode in an elegant way. One way to do that is to sum the resummation of the perturbative series, which I wrote down over here. Sum that over SL2Z images. And what you get is the following. So notice that we get a sum over two integers, m and n. There's an integral, a one-dimensional integral over some kernel, and that kernel is the SL2Z Borel transform. So what we learn from this is that there's the form that D'Origoni, Green, and Wentz wrote down wasn't specific really to that observable. Really, it's just taking advantage of the fact that the cusp form overlap vanishes. So that in fact, this lattice integral representation persists for pretty general CFT observables as long as the cusp form overlap vanishes. And moreover, the kernel, it ascribes a physical meaning to the kernel of that transform, which is the SL2Z Borel transform of the zero mode.
So because of this Borel transform trick, you could really get that B from the kind of strict perturbative sector, not including any instanton, anti-instanton.
Exactly.
Those will pop out of the inverse.
Yeah, although remember that FNP for those guys was 0. I wrote it down, yeah.
So what characterizes the class of observables for which this is true?
Yeah.
Is it like BPS protected thing?
We think it has something to do with the amount of supersymmetry preserved by the observable, but the honest answer is that we don't know. We don't know how, in which cases, for which kinds of observables, this property holds.
So I mean, I asked the question up at the beginning, whether you're going to think about things that are SL2Z invariant or representations of SL2Z. And I would have thought that if I pick sort of a generic observable in Yang-Mills theory, it's going to undergo all kinds of operator mixing as I run the renormalization group or as I change tau.
Right.
And so I wouldn't be looking at invariance, but I would be looking at some ginormous collection of observables which mix with each other as you run around in tau space. So I was just wondering how this formalism or the sorts of things you're pursuing might extend to those classes of things.
I think that the operator mixing thing isn't such a big deal as long as you define the observable carefully enough. So I gave the example earlier of instead of talking about the Kanishi, talk about the lightest SU4R singlet scalar operator, the dimension of that thing. And I think that quantity should be, for example, SL2Z invariant. But it's true that if you're interested in a quantity that transforms in some ginormous representation of SL2Z, I don't know how to directly apply this technology. If it transforms covariantly, then I do know how to accommodate that. But if it transforms in some big representation, I don't a priori know how to accommodate that. This framework.
This is Jeff Harvey from the Sky. Could you just clarify what you mean here? So, I mean, there are certainly objects like modular forms that transform non-trivially under the modular group that are not invariant. Is that what you have in mind? Or when you say a ginormous representation, are you thinking of some vector representation of the modular group?
Well, what I had in mind was something that transforms with a definite weight under SL2Z.
Okay. So like weight n and m under tau and tau.
Exactly. Yeah, that I do know how to accommodate. Basically, you just multiply by an appropriate power of imaginary part of tau, and that's invariant. Now, the statements about square integrability get messed up a little bit, but they can be taken care of.
But is there no situation under which the holomorphy or anti-holomorphy of the observable in tau plays an important role?
Yeah, in this discussion, I think basically no, because if you have a holomorphic observable, that'll have some polar behavior, right, at the cusp, which means it's not square integrable and it won't fit into our framework. So I guess I would say that the kinds of observables I'm interested in are almost by definition not purely holomorphic or anti-holomorphic. Just because they won't have a well-defined free limit, they'll blow up as you approach the cusp. There'll be some polar terms, and really, I think the SL2Z technology would be overkill. Like we know that those things are fixed by their polar behavior.
Okay, thanks.
Okay, thanks.
So, just one more
Yep.
question. So, usually things that can be, for which the Borel resummation works are also kind of special, right? You're basically saying that they're almost defined by their perturbation series. Yeah. Generic things in, where there are non-perturbative phenomena like instantons and so on, you could say probably not Borel summable. So can you say a little bit more about?
Yeah, and we'll actually get to that when we get to large N, because we'll see situations where observables aren't Borel summable, essentially as a consequence of SL2Z. Here what I had in mind was observables whose weak coupling expansion is Borel summable. So if I define it this way and then strip off the lambdas, there's some finite radius of convergence. That's probably not. It's certainly not always the case, but at least for observables, and I think there's a pretty broad class of observables for which this is true. Then you can obtain it entirely from its perturbative expansion in this way. I'm going to skip this slide in view of time. The basic upshot is that SL2Z tells you that if the zero mode is SL2Z Borel summable with some finite radius of convergence, then it's also true for the higher instanton sectors. And there's this very simple formula that relates the radius of convergence in the K instanton sector to that of the zero instanton sector. Okay, so it's finally time to talk about large N. I should ask, are there any questions before I move on? Okay. So in this talk, we'll be concerned with the 't Hooft limit, where we take N to infinity and fix the 't Hooft coupling. And of course, in this limit, the perturbative 1/n expansion organizes into a genus expansion. At each order in the genus expansion, there's some non-trivial function of lambda, the 't Hooft coupling. And in this section, I'm exclusively going to be talking about the zero mode for the reason that higher K instanton sectors are inherently non-perturbatively suppressed. So I'm going to restrict my attention to the zero mode. And that's nice because then I get to ignore cusp forms. So we basically played the exact same game as in developing perturbation theory, except now we consider the 1/n expansion of the spectral overlaps. And I'm going to set FNP to 0 for now, just to clarify the presentation. It's not an essential, turning it back on is not hard to do, and if I have time, I'll discuss how to do it. But just to simplify to streamline the presentation, I'll turn it off for now. So you have this general form for the zero mode. It's basically the same as before. This is morally the zero mode of the Eisenstein series. Now FP has a genus expansion. And you play the same game. To develop, say, weak coupling perturbation theory at small lambda, you deform the contour and ask what is consistent. And that will lead to even stronger constraints on this overlap FP, it turns out. So, you can see it from here. SL2Z tells you that in addition to this term, which will generate a power series in lambda, there's this funny partner, which reorganizes the 1/n expansion. So in particular, it tells you that FP needs to cancel the poles of the sign at integers, and it is allowed to have poles at half integer values of S, just for consistency of the genus expansion. Very good. So at the very end of the day, what you find is the following. So as expected, the zero mode admits an expansion in the weak coupling limit that just proceeds in powers of lambda. And here the coefficient is just some residue function that you obtain by computing the residue of this quantity at the appropriate pole. Its explicit form doesn't matter, just know that it's some known residue function determined in terms of FP. And the constraints I mentioned earlier lead to a very rigid structure of the strong coupling expansion. So where you instead expand at large lambda rather than small lambda. So there's a constant term, unlike the weak coupling expansion, just a constant. The constant involves the average, and that will be important later. And then there's a genus expansion. So an interesting consequence of what I said earlier about the structure of the poles in FP associated with the well-definedness of the weak coupling expansion is that the strong coupling expansion proceeds in half integer powers of lambda, or 1 over lambda. And moreover, because of the presence of this SL2Z partner term, you get these extra terms which are suppressed in 1 over n squared, but that come with positive powers of lambda. So this is what I meant when I said that SL2Z reorganizes the 1 over n expansion. And these actually have a nice, these have been observed before, and they have a nice interpretation. They're needed for the renormalization of the 1 over n expansion at strong coupling. Holographically, you can think of them as associated with the stringy regularization of loop divergences in supergravity. So at g equals 0, m equals 1, this goes like root lambda, and you can think of that as the associated with the r to the 4 regularization of one loop supergravity from string theory, of course. Okay, I appreciate that was fast, but the general upshot is that the weak coupling expansion proceeds as it should. And the strong coupling expansion has this sort of rigid form with half integer powers of 1 over lambda and these extra renormalization terms. And something else that will be important is that these coefficients are related. Note that it's the same coefficient that appears down here, just at positive argument rather than negative argument. And so we'll see that the asymptotics of the weak coupling expansion will have something to say about the asymptotics of the strong coupling expansion.
So no supersymmetry is needed for that statement. What's going into that other than invariance of the observable?
Other than SL2Z, you mean?
Well, that's what yeah. I mean, that's a given.
The other place that n equals 4 enters is the interpretation of this constant term here as the ensemble average, because remember the relation between the modular average and the ensemble average required maximal SUSY.
Yeah.
But other than that, I'm really just using the structure of perturbation theory on the one hand and SL2Z on the other.
It seems weirdly strong to be able to say that small.
That's SL2Z. It's SL2Z, I think, doing the heavy lifting there, and of course the structure of perturbation theory, the weak coupling limit.
Sorry, but if there were mass forms or F non P, FNP, wouldn't the formulas be different?
FNP would modify them in a simple way. We took that into account in the paper, and Moss forms would not really affect the discussion because they're inherently non-perturbative, so they don't affect the perturbative series. Because remember, the Moss forms have no zero mode.
This is the zero mode at strong coupling.
Yeah. But I think it's rather general to restrict to the zero mode in the large n limit because of the non-perturbativeness of the higher instanton modes. So this fact about the weak coupling and strong coupling expansions being sort of tied together through this common residue function, that rears its head here. So if the weak coupling expansion, so the weak at Tuft coupling expansion of the observable is convergent, then that on its own is enough to imply the existence of non-perturbative effects, both at large n and at strong coupling, so large lambda. And I should emphasize here, these are at fixed orders in the genus expansion. And moreover, the non-perturbative scale is set by the radius of convergence of the weak coupling expansion. And that basically follows directly from the fact that it's this common residue function that appears here. Now, it turns out that in n equals 4, there's a radius of convergence that's quite common, or generic even, pi squared. I don't fully understand the reason for this, but I think it has something to do with like combinatorics and the planar theory, but don't quote me on that. Anyway, for a large class of observables, this is the radius of convergence of the weak coupling expansion. And that implies the existence of non-perturbative scales that are set by lambda and what we call lambda s, which is an S-dual of coupling. It's like n over g squared instead of n times g squared. And they're given by the following. So the former is just e to the minus root lambda. And now this is just e to the minus 2 pi times the tension of a fundamental string. For the S-dual coupling in the limit where n is much bigger than lambda, i.e. lambda s is very big, then you have non-perturbative corrections with this strength, e to the minus root lambda s. And that is given in terms of the tension of a D1 brane. And for this reason, the reason of this scaling, we associate these effects with either fundamental string or D1 string worldsheet instanton effects in ADS5 times S5. So perturbation theory has to be supplemented by these worldsheet instanton effects if the weak coupling expansion is convergent. And here's some cartoon that I stole from this paper on the octagon by Bargier, Coronado, and Vieira, where you have some worldsheet pinned to the boundary of ADS, with 4 points pinned to the boundary of ADS, representing some of these worldsheet instanton effects. Any questions?
And these are distinct from the instanton effects.
That's right, which you associate with the gauge theory instantons like QQ bar. That's right. Okay, so here's a slide where I say basically the exact same story goes through for FNP not equal to 0. We treated this carefully in the paper, but the basic message is that, so remember at strong coupling, the expansion in powers of lambda proceeded in half integer powers. If you turn on FNP, that gets relaxed a bit and you can have integer powers of 1 over lambda. And in fact, you can take the presence of those things as a signal that FNP is not 0. And at the end of the day, it slightly modifies the form of the strong coupling expansion, but not really in an essential way. So here now I have integer and half integer powers of 1 over lambda, and the renormalization terms can have a slightly more intricate form, but the basic structure is preserved. Alpha here is some half integer, it's bounded above by m. Anyway, as before, A and B are both computable residues. And again, this is some constant. Okay, this general form here and the one I wrote down earlier equivalently are kind of remarkable equations. In particular, if you look at the 1 over n expansion of the average, which remember appeared in this constant C of n, then, okay, I wrote it down earlier. This is the other term that appeared in Cn, just with the opposite sign. So here I call this part, this is the leading part of the average at large n. There's some subleading part, and the subleading part cancels when you combine it with the other stuff in C. So what is the point? The point is that in the large n limit, the large n limit of the average, which I denote with these double angle brackets, that's the only term that survives in the strong coupling limit, because everything else is suppressed either by powers of lambda, 1 over lambda, or by further powers of 1 over n squared. And this has rather striking holographic consequences. So in other words, we've arrived at a large n equivalence between strong coupling on the one hand and ensemble averaging in the other. In other words, at large n, the large n limit of the average is equal to the strong coupling limit of the observable, which is otherwise known as the value of the observable in type 2b supergravity on ADS5 times S5. So really, it's an extremely basic consequence of, I mean, not even this form, but this form of the strong coupling expansion. And so again, we have these two pictures of the two ways to think about supergravity, both as a strong coupling limit and as a large n ensemble average. And from here, it's clear that there's a sense in which this extends to all loop orders, so all orders in the genus expansion, because the same structure holds. In other words, the strong coupling limit of what I called OG the observable at G loops is given by this large N limit of the genus G part of the average. Of course, the right-hand side is finite, and if you just compute the left-hand side in supergravity, it generically won't be. And that's because it needs to be understood as renormalized in the same sense as this observable by the presence of these renormalization terms. So in that sense, the correspondence extends to all loop orders. Are there any questions? Okay, so obviously nothing I've said has disturbed the conventional holographic paradigm. You know, each instance of n equals 4 is still dual to type 2b string theory on ADS5 times S5. It's really only the strongly coupled theory at large n, which is dual to bulk supergravity, that emerges as an ensemble average. And I want to emphasize that that ensemble average is emergent. But as in the low dimensional dualities, which we'll discuss in a moment, the averaging generates a rather simple bulk theory. It's just supergravity. And it's extremal in the sense that it has the largest gap consistent with the symmetries. You might hope that there might be some scenarios where the average, as a, it's kind of a coarse-grained observable, maybe it can be studied more easily than, the strong coupling limit, which requires control over strong coupling dynamics. And potential inspiration for this is the Narain duality, where the average spectral gap at large central charge was essentially manifest in the ensemble average. But if you try to show typicality of that by sampling random Narain theories, it's basically impossible. And a final corollary is that any observable that diverges in the strong coupling limit can't be modular invariant. And a famous example of such an observable, which goes like lambda to the quarter at strong coupling, is the Kanishi anomalous dimension. And that's just for the reason I described earlier.
So for instance, the energy of the lightest string state. Sort of in this limit, it seems like you've thrown out every vestige of stringiness.
Well, they're still there. It's true that the alpha prime corrections, which are encoded in these 1 over lambda corrections, those of course are thrown out because I'm talking about supergravity. But there is still a sense in which the 1 over n structure persists, because I can talk about the 1 over n expansion of the average, and that corresponds to the G loop supergravity observable. But yeah, it's true. I mean, I'm talking about supergravity, so I have in this correspondence thrown out the stringiness.
There's some kind of finiteness of n equals 4 of maximally symmetric supergravity on ADS5 times S5 that's implied by this?
You say a bit more, what do you mean?
Well, people talk about various divergences and scattering in
that's what you mean. Yeah, that's a good question.
If I interpret the equation the other way, does it imply that?
I thought you had times that renormalize.
At higher loops, that's true. That's true. There's a renormalization implicit in this.
But there's some unique there's some unique single out.
Yeah, it seems to single out a renormalization
it seems to
scheme.
single out a scheme that makes everything finite.
Yeah, that's interesting. That's suggestive that it's consistent with the stringy regularization, but it's not a proof that it's a unique one. It just seems to be picked out by the spectrals.
Still confused. So I have an ensemble of things, many of which, the generic element of I would have thought the generic element of the ensemble would be a string theory. So that when I do an ensemble average,
Indeed,
there should be some vestige of stringy results still there. So I understand that the strong coupling limit is explicitly non-stringy because lambda goes to infinity, couples all the string states. But the ensemble average I would have thought would work the other way.
Here's a vague piece of intuition, which isn't exactly correct, but may be a useful heuristic. At large n, if you define the lambda in terms of g squared in the usual way, most points in moduli space are in the strongly coupled limit in the sense that they scale with n. If the coupling is order 1, then lambda at large n is order n. So most regions of moduli space are strongly coupled in that sense. I think that's a heuristic for thinking about the origin of this correspondence.
No, okay, so that's related to another question which I've refrained from asking, so maybe now is a good time.
Go for it.
Are you imagining only looking at observables which are expanded around the SL2 conformally invariant vacuum? Or so for instance, one part of the spectrum that we're very interested in is the spectrum of states whose energies grow with n squared,
Yeah,
and like black holes.
yeah.
Or string states whose energies grow with n. So if I ask about observables in that regime of the spectrum, then I think that would call into question this sort of a statement.
Yeah, I mean, at a technical level, what you need is SL2Z invariance, and that it has a well-defined genus expansion. Some of these observables sensitive to, high energy black hole states may not have a sensible large N, like genus expansion in the same sense as these other observables. That may be one way to reconcile it, I'm not sure. But yeah, the only ingredients really that went into this are the structure of the 't Hooft limit and SL2Z.
Well, on the supergravity side, I guess I would have said, well, you might say there's some Euclidean black hole solution when we work in some limit where stringy corrections to the black hole solution are somehow suppressed. So maybe you might some statement like that.
You mean other than just the supergravity limit, or
Well, there is a well-defined supergravity limit. It's just
Yeah.
the Euclidean black hole solution, say.
Yeah.
And so maybe you would look for some equivalent statement there that somehow taking the large n limit is forcing you to classical supergravity around the Euclidean black hole, and the stringy corrections to that are somehow being thrown away as well.
Yeah, I see where you're getting at. I don't think it's important for what I'm saying that we're expanding about the vacuum in that sense. But it all has to do with the structure of the 1/n expansion of the observable, so I'm not totally confident how that proceeds in the example that you have in mind.
You somehow enhance your symmetry to SL2R in this limit.
Yeah, right. Yeah, but you don't really see that.
I don't see any real sign of that. I mean, that might be part of the answer to the Clay's question of whether or not there is a theory that you could have defined that's consistent. Maybe SL2R is enough to fix the kind of counterterms you have to have.
Yeah,
Yeah, I see what you're getting at. I mean, I should say that this is kind of weird, and we don't claim to fully understand it. There's some puzzling. Well, I'm basically out of time, but there's some puzzling aspects related to the statistics in the ensemble that I'll try to say some very brief words about that we find quite confusing. So obviously, given this correspondence between ensemble averaging on one hand and strong coupling on the other, we're well motivated to study statistics of observables in this ensemble. Tried to note by these little dashed line correlating 2 points in the moduli space. So the spectral decomposition cleanly picks out the ensemble average. There's the ensemble average plus what we call O spec, which is, it averages to 0, and it's what contains all the coupling dependence. So for example, you can compute the variance of an observable very straightforwardly in terms of these spectral overlaps. It's just the average of O spec squared. And it's given by this nice formula in which the second moment in tau space on the left-hand side, the variance, is given by this expression involving the spectral moment, the second moment in spectral space. Now, confusingly, at large n, well, it's not confusing that the variance is parametrically suppressed compared to the mean squared. That's expected, and one observes a structure like this in like random matrix theory. But in the gravitational language, it's puzzlingly large. Remember, n squared is like 1/g. And we find that the variance is down compared to the mean squared by a power of 1/n. And that's confusing. In a sense, it's neither non-perturbative, which you might expect if the variance had something to do with connected bulk configurations, nor is it really purely perturbative because it's 1/n, not 1/n squared. So this we find very puzzling, and we're trying to understand it better. And moreover, the 1/n expansion of the variance is divergent if the weak coupling expansion is convergent, and that leads to non-perturbative effects with this funny strength involving e to the minus root n, which again are also quite puzzling from the gravitational point of view. So I'll conclude with some comments. Obviously, this ensemble, this emergent average duality is interesting in light of recent developments in low-dimensional quantum gravity, where very simple bulk theories based on the gravitational path integral are dual not to particular quantum systems, but statistical ensembles of quantum systems. Famous examples being JT gravity and this recently developed very exotic theory in 3D W1 gravity. And a common thread in these works, holographically, is that space-time wormholes play an important role. And this leads to some natural questions and even the conventional holographic dualities that go by the name of the factorization puzzle. You can think of this puzzle as having both bulk and boundary components. The first is what other bulk ingredients are needed for factorization of multi-boundary observables? Beyond the gravitational path integral, what other bulk ingredients do you need for a theory to factorize? And I have nothing to say about that in the context of n=4. I'm not going to be able to identify the stringy degrees of freedom that lead to factorization of some specific observable. But on the other hand, on the boundary, if you look at a product of observables in two decoupled CFTs, you could ask why there are contributions that appear to correlate them. And when and how do those things appear? And more broadly, where are wormholes hiding in the bootstrap? And this is the question that we have a bit more of a handle on. So this large N equivalence between the average and the supergravity value suggests a gravitational manifestation of these ensemble statistics. And the question we want to know is how much does semi-classical ADS5 times S5 really know about those ensemble statistics? So here we have this cartoon where we have two abstract depictions of the moduli space. We're looking at the variance, which correlates the two copies. And we're asking if there's a sense in which at large N, this cartoon is geometrized into a space-time wormhole. So the short answer is we don't know, but there are some suggestive equations you can write that sort of resonate with recent work on factorization in these low-dimensional dualities, where they identify additional contributions, additional saddles whose role in life is to restore factorization. These go under the name of half wormholes. So here we have O is the average, otherwise known as supergravity, plus O spec. And we can morally, but not precisely, think about this as the half wormhole in the sense that it provides the coupling dependence responsible for factorization. So to probe the ensemble statistics, we look at higher powers of O spec. So for example, O spec squared, there's a variance which corresponds to coupled boundary theories. So in some sense, it corresponds holographically to a space-time wormhole. And then there's everything else, which encodes the coupling dependent fluctuations around the variance. And of course, in any member of the ensemble, these two compete and conspire to give a factorized answer. But the variance is there. And I think it's not totally tautological because the average is not just some random quantity, it's the supergravity value. Again, this is just what I said earlier. And the question we want to answer really is, does the variance have a space-time wormhole interpretation in semi-classical gravity? And as suggested by this recent paper by Schlenker and Witten, maybe there's some sense in which the answer depends on the type of observable. So sorry for going quite a bit over time, but I'll just conclude with some future directions. At the topmost, the most urgent of which is to understand to what extent this story could generalize to other string or M theory vacua. We'd love to have more data by looking at other observables and other S-duality groups. And from the bulk, it's clear, I think, that we need to better understand the bulk perspectives on both the non-Borel summability of ADS5 string theory and the semi-classical meaning of the variance. It would be great to combine the spectral approach with other approaches to bootstrap. And more generally, it would be nice to more systematically investigate the statistics of CFT data over conformal manifolds. There's some nice work done here in Chicago by the group here in the context of Clavier signal models. And finally, it would be great to understand if there's any concrete connection between cusp forms and arithmetic chaos manifesting in more conventional forms of chaos in n=4. So I'll end there. Thanks a lot.
Questions?
what sort of observable you'd have to look at in order for you to get something that looks like the supergravity around the non-vacuum solution?
Like what Emil.
Yeah. Like heavy operators.
Yeah, presumably some observable. Yeah, one thing actually good. One thing that we are interested in investigating is thermal observables, and these are sensitive to the statistics of high energy states. Something like the thermal partition function on S3 times S1, thermal 2-point function, those sorts of things. That may have something to say about black hole physics, but yeah, the discussion I presented in this talk was sufficiently general that you really can't, from the formalism, distinguish between that and some basic perturbative observable.
Was the fact that things were integrated, like you were looking at integrated correlation functions, it
Yeah.
wasn't really crucial for anything?
Not really, other than they had a chance of being simple and comprehensible across the moduli space. Like for each value in n and tau, it's a number instead of like a 4-point function. So it really is, for simplicity and tractability. Yeah, I mean, obviously it would be great to have a handle on like unintegrated correlators, or any less coarse observable that would be more sensitive to like operator statistics in the ensemble. The integrated correlator is admittedly a kind of coarse observable from that point of view.
So, we're trying to imagine extending this to other instances of ADS CFT.
Yeah.
In ADS 3 times S3, there isn't just one cusp of the moduli space, there's one for every factorization of big N into numbers of 1 branes and 5 branes.
Yeah.
So, so is there a fantasy for how that should work? And then the second question is, what about for ADS 4 times S7 or ADS 7 times S4 where there's no moduli space?
Yeah. In the latter case, we really don't have any concrete proposal how it might work. We really do need, like a finite conformal manifold. The ADS3 case seems like probably the most concrete example to think about next. There are a lot more moduli for one thing, a lot more directions you can average over, and maybe to get a simple bulk dual, you don't have to average over all of them. It could be that there's like a gravity direction on the conformal manifold that's privileged.
There kind of is. If you just want to freeze, say, the K3 or T4 moduli and talk about the same sort of dilaton axion subspace of the modular space.
Yeah, I mean, there are a lot of.
But the point is that within that space, the modular group isn't SL2Z. It's a finite index subgroup.
Right, and for these other
instantiations,
instantiations,
which is why there are these other cusps.
At these other instantiations of ADS CFT, you have to decide whether you want to average over the like U duality group, like like the analog of S duality, or whether you want to average over the conformal manifold. And it's not clear which is the right thing to do, if either. And if you do average over the conformal manifold, then there are also a lot more moduli, and you have to decide which directions you average over. So yeah, there are a ton more possibilities. We laid some of them out in the paper, but we don't have a concrete proposal.
For these other backgrounds that you mentioned, such as, let's say flat space, types of new flat space, I mean, you also have SL2Z duality there.
Yeah, I mean, ultimately that's where the SL2Z of ADS 5 times S5 descends from. I had in mind ADS CFT instantiations rather than flat space.
But is there like a similar statement that instanton sectors are fixed by perturbative sectors?
Oh yeah, you could in principle do the harmonic analysis as long as the observable is well defined in the free string.
We can do the S matrix.
Yeah.
It's activity.
Yeah.
Like in 10 dimensions.
Yeah, so similar technology would apply, but the interpretation would probably be a little bit different.
I mean, there's kind of a matrix theory definition of that in terms of what, ABJM or maximal, whatever, however you want to call them, the maximal, the infrared fixed point of Yang-Mills in
Yeah.
3D on the torus, on the T-torus. And that tau is supposed to be the target space tau, type 2B.
I see.
You could do something similar that maybe one can.
That's an interesting suggestion. We didn't think about that at all. We sort of just assumed that there was nothing we could do with the ADS4 style dualities. It's interesting.
Let's thank Scott again.